Hi, today we're going to learn about more math involving gases, where we're talking about the ideal gas law derivations, partial pressure, and Graham's law of effusion. Last class, we did a lab where we only measured the gas under one condition. And we learned from that the ideal gas law is what we would use as opposed to that of the combined gas law, which was PV equals nRT. Friendly reminders that R is our universal gas constant, and which one we use depends entirely on what unit we have for pressure. T is our temperature, that always needs to be measured in Kelvin. V, our volume, always needs to be measured in liters. Our pressure can be in either ATM or kPa, which is kilopascals, or torr/millimeters of mercury. The reason why those ones are slashed is because they are equivalent. Their standard values are both 760. And N, which is what we're going to be emphasizing now, are our number of moles. Earlier this year, we learned about a mole conversion, where anytime you have the mass of a substance and you want to convert it into moles, you have to divide it by its molar mass. Again, mass divided by molar mass will always give you number of moles. If you forget what that means, mass is measured in grams, molar mass is measured in grams per mole. The grams will cancel each other out. Moles is the denominator of the denominator, making it the numerator. So our math is justified. So the first derivation that we're able to write from the ideal gas law is the following. PV is equal to mRT divided by mm, big M, little m, for molar mass. Now, since we're talking about gases, it's next to impossible to measure the mass of a gas. So what other property are we able to utilize? We can tap into the density. We've learned earlier that density is equal to an object's mass divided by the amount of space it takes up, which is the volume. Looking at our equation here, if I divide both sides by volume, I get P is equal to mRT divided by V mm, and the mass over volume can now be rewritten as density. So the final derivation of the ideal gas law is as such. Pressure is equal to the density times the universal gas constant times the temperature divided by the molar mass. Do you need to memorize these two formulas? I don't think so. You can figure it out by, just logically deducing what we just did together. The one you'll be given on the reference packet is the original PV equals nRT. Moving on. Another concept that we did in lab, unknowingly to you at the time, is called Dalton's law of partial pressure. Dalton's law of partial pressures. Looking at the visual, we have one vessel filled with oxygen gas and a second vessel filled with nitrogen gas. The pressure of each of those gases is measured. The two vessels are combined into one, so we now have a mixture of oxygen and nitrogen. How did the individual pressures of the two gases compare to the pressure of them mixed together? Well, wouldn't you know it, it winds up being the sum. That is Dalton's law of partial pressures. We can generalize it with the following formula. The total pressure, or P total, is equal to the pressure of gas 1 from the mixture plus the pressure of the second gas in the mixture plus the pressure from the third gas in the mixture, if there is one, plus the pressure from the fourth gas in the mixture, etc. The sum of the individual gases in the mixture will equal the total pressure of the mixture. Where did we see this in the lab? We saw this when we were trying to isolate the pressure of the gas that was produced in our lab experiment. Let's look at a different experiment and analyze what was going on. In this experiment, we have some solid potassium chlorate in a test tube. That's the only thing reacting. What we've learned so far is when we have one reactant, it's going to decompose. The decomposition of a chlorate will give us the metal chloride and oxygen gas. We could prove the existence of the potassium chloride because most likely the potassium chlorate will change color. But we're not able to prove the oxygen gas as easily because it's an invisible and odorless gas. So if we were to put a stopper in there and poke a hole in it and feed a tube through it and feed that tube into a bottle of water that's filled all the way to the tippy top, as the oxygen gas is produced and it's less dense, it's going to rise to the top of the test tube, go through the tubing here, and enter the upside down bottle. It will continue to rise all the way to the top because, again, gases are less dense. And those gas particles, every time they make collisions, are going to start to collide with the water. And the water will now get forced out of the bottle into the larger beaker here. And at the end of our experiment, what we're going to need to do is get the level of the water inside the bottle to be equal with the level of the water outside the bottle. Because at that point in time, the pressure of the gases of the atmosphere, those are the ones that would be pushing down on the water in the large vessel. That's going to be equal to the pressure of the gases that are inside the bottle. What's in the bottle? Well, oxygen gas and something else. The something else comes from the water. There are a few particles of the liquid at the surface evaporating into the gaseous state. Once they're in the gaseous state, when those particles now collide, they're exerting a pressure. So the pressure of the atmosphere pushing down on the outside is going to be equal to the pressure of the water vapor on the inside, as well as the pressure from the oxygen gas that was collected. So you may remember that we needed to know the temperature of the water because the temperature is dependent upon how many liquid water molecules will move into the gaseous state, and the more gas particles you have, the greater your pressure. We were doing Dalton's law of partial pressure, and we didn't even know it. Finally, our last new material for today is Graham's law of effusion. Graham's law of effusion. Effusion means gases escaping through a pinhole-sized opening. This law can also be used to explain diffusion, which is the natural mixing of gases. Remember, gases are in constant, rapid, random motion, and they travel in straight lines until they make collisions with either each other or the walls of a container, upon which they will change direction. Graham's law came about as a result of two gases reacting together. One gas is nitrogen trihydride or ammonia. The other gas is hydrogen monochloride. The cool thing about these two gases is that when these molecules collide, they are able to form a precipitate, ammonium chloride. So a cotton ball drenched with each of the separate, or 2 cotton balls drenched, one with each of the different reactants, were plugging the openings of a long glass tube. And the hypothesis was that, well, these gas particles of NH3 were going to travel down the tube because of diffusion, and the idea was that the particles of HCl were going to travel down the tube because of diffusion, and eventually they'd reach a point, most likely in the middle, where they would collide, and that's the point where the precipitate would form. However, experimental results showed that that wasn't the truth. The actual precipitate formed here. The HCl particles did not travel as far as the NH3 particles. Why? Well, Graham came to the conclusion that it must have to do with the size or the mass of the particles. He concluded that the lighter particles, the lighter gas particles, traveled farther than the heavier ones. And it didn't have to do with the mass of the sample, but rather the molar mass of the matter. NH3 has a molar mass of 17.04 grams per mole. HCl has a molar mass of 36.46 grams per mole. Since the HCl is a bigger or heavier molecule compared to the NH3, it's not going to travel as far, which explains why the formation of the precipitate happened closer to the HCl. How can we explain this mathematically? Well, the rate that a gas will move, whether it's through a pinhole-sized opening or just left to its own devices, it's inversely proportional to its molar mass. Oh, the square root of its molar mass. The rate of effusion of a gas is inversely proportional to the square root of its molar mass. So if I wanted to compare the rate of gas 1, which would be NH3, compared to the gas 2, which would be HCl, I'd have to take the square root of the molar mass of the gas of HCl divided by the molar mass of the gas of NH3. And that's going to give me the rate of effusion, how many times faster or slower that molecule will move. Thank you very much for listening to today's lesson. When we get together in class, we'll work through problems so that we